Okay, so last time we were talking about three-dimensional vectors within the context of 3D geometry. And then we looked at a way of computing a certain product, a scalar product of vectors called the dot product or scalar product, but commonly called the dot product, where you multiply two vectors together to get a scalar. Well, tonight we're going to look at a different product called the cross product, with the result of taking the cross product of two vectors being another vector that is perpendicular to the two vectors. And then we'll take a look in section 12.5 of some vector valued functions in three-dimensional space. Curves in three-dimensional space using vector valued functions. All right, let me turn on my pen here. All right, so here's kind of the idea here. One application where we would often see the cross product is in the ideal of a torque. Now, torque is the result of some twisting motion. Torque is determined by the length of the lever, by the magnitude of the force that's applied to the end of the lever, and then by the angle between the lever and the force. All right. The torque vector, because torque is a vector valued function, always points parallel to the direction of the twisting. And it has a certain magnitude, of course, that's dependent on the angle, magnitude of the force applied, and the length of the lever. The lever vector is given the vector named r as like a radial length. And we have our friendly force vector there and our angle theta. So what we're going to, and we'll return to the torque, but hopefully this kind of a motivation to come up with some sort of product between the radial vector and the force vector in order to produce the torque vector. Okay. Now, remember that our three-dimensional rectangular system, XYZ system, is right-handed. Well, when you take the so-called cross product of two vectors, u and v, that you're going to get a vector according to the right-hand rule. So imagine that you've got two vectors u and a vector v and some angle in between them. And you're going to take the cross product. And by the way, here's the symbology for it. You just have a little multiplication symbol in between. We typically call it u cross v. Well, u cross v is going to be a vector that is perpendicular, orthogonal to both u and v, according to the right-hand rule. Point your fingers in the direction of the first vector u, and you curl them in the direction of the second vector v, and then your right thumb is going to point in the direction of u cross v. Which, by the way, is a useful thing to know, because there's going to be times when you need to come up with a vector that is perpendicular to both those two vectors u and v, and what easier way to come up with a perpendicular vector than to take the u cross v. So for example, suppose that we've got a plane, some plane out there in three-dimensional space, and you need to come up with a vector that's normal to that plane. Well, just find two vectors that are on the plane and take their cross product, and then you'll have your normal vector, for example. All right, anyway, so here's how we can define the cross product of two vectors. Well, I'll show you how to actually compute the actual cross product here in a minute, but at least the magnitude of the cross product can be written as the magnitude u and the magnitude v times the magnitude v times the sine of the angle between those two vectors. And you want to know the direction of u cross v? Well, either be, use the right-hand rule going up or down. Of course, use your right-hand rule. That'll give you, your thumb will point the way. But I'll actually show you the algebraic way of computing. This is more of a geometric way of computing the magnitude of the cross product. Now, two vectors that are parallel will have a cross product as the zero vector. In order for your cross product to actually produce something interesting, the two vectors have to meet at some angle other than 0 or pi. Because, hey, what is the sine of 0? Sine of 0 is 0, so the cross product will really produce nothing if theta is 0 or pi. Sine pi is 0. However, though, if the theta is pi over 2, then you'll kind of get the full value of the cross product if the two vectors are perpendicular to each other. So this just kind of repeats what I just said. If the two vectors u and v are parallel, that is equivalent to saying that the cross product is the zero vector. Here's an interesting factoid, is that if you have some parallelogram out there on a plane or something, and u and v are vectors that define two adjacent sides of a parallelogram, then you can compute the area of that parallelogram by computing the magnitude of the cross product of u and v. So suppose that here's vector u here, and then vector v, and you put their little tails together down here, then you complete the little parallelogram here. So you've got this parallelogram. Well, the area of this parallelogram is given by the magnitude of the cross product of u and v. I still haven't showed you how to actually compute the cross product yet, but I will. As a corollary to number 2 here is, in 3 dimensions, if you have a triangle in 3 dimensions, 3-dimensional space, we want to find the area of that triangle. Well, you can find the triangle as half the area of a parallelogram. So find two vectors that form adjacent sides of your triangle, take their cross product, then take half the magnitude of that cross product. That will give you the area of the triangle. Any questions so far? Here's a kind of a little proof for the parallelogram area thing. Remember, for a parallelogram, area is base times height. So the base here would be magnitude u, height would be magnitude v times the sine of angle theta. Let's take a look at an example number 1 here, section 12.4. So, example number 1, we've got a vector u given by components 1, 1, 0. And we've got vector v given by components 1, 1, square root of 2. And we're supposed to find the magnitude and direction of u cross v. Now, we don't know how to specifically calculate u cross v, but we can find the magnitude of u cross v. Remember, magnitude of u cross v is magnitude u times magnitude v times the sine of the angle between the two vectors. Now, let's go ahead and calculate magnitude u, square root of 1 squared plus 1 squared plus 0 squared. And that's, square root of 2. Calculate magnitude v, square root of 1 squared plus 1 squared plus square root of 2 squared. And what would that be? 2. Right. So now we just need to find theta. So let's take a look at this picture. This is figure 12.58 in your textbook. Here's vector u, and here's vector v. All right. What is this angle in between those two vectors? Pi over 4, right? You can use your trigonometry skills to figure that out. But the angle between u and v is pi over 4. So let's go back. Theta is equal to pi over 4. So magnitude of u cross v is going to be magnitude u, which is square root of 2, times magnitude v, which is 2, times the sine of pi over 4. Sine of pi over 4 is 1 over square root of 2. So the result, of course, after you cancel the root 2's, is 2. So there's the magnitude of u cross v. And then we could visualize the direction of that cross product. All right, so here's x, there's y, and so u comes out in this direction, v goes up here, and then do the right-hand rule, and the u cross v will point out this in this direction right here. So that's the green vector. Of course, it's kind of hard to draw in 3 dimensions. Maybe someday we'll have visualization tools in 3 dimensions now. Maybe we'll have holographic presentations here before I retire one day. We'll see. That'd be kind of cool, huh? Any questions so far about cross products?
How would you do that with your right hand rule and with your actually using it? Your fingers go to the one.
Well, your fingers will point in the direction of the red vector. And then your curls will curl, your fingers will curl in the direction of the blue vector. And then your thumb will naturally point in the direction of the u cross. All right, some algebraic properties of the cross product. Now, the commutative property does not hold. U cross V is not the same as V cross U. Now let's think about that. U cross V is actually the opposite, or the negative of V cross U. Because of the right-hand rule. Remember, your fingers point in the direction of U, and they curl in the direction of V. Huh? But if then you were to take V cross U, your fingers would then point in the direction of V and curl in the direction of U, so your thumb would point in the opposite direction. So U cross V and V cross U would have the same magnitude, they would just point in opposite directions, right? Hopefully that makes sense. All right, the rest of this is fairly straightforward. Suppose that you've got a scalar multiple of vector U crossed with some other scalar multiple of vector V. Well, look, you can move these scalars around to the other vectors, or you can just pull them out completely from the cross product. Here's, for 3 and 4, we've got two different versions of the distributive property. You've got U cross the sum of two vectors V and W. Then you can do the cross products first with U and V and U and W and then add. Or you could do that on the front end. You can do the addition first and then cross with W, which would be the same thing as U cross W plus V cross W. Both of those properties work. And from time to time, those will be useful, but not very often, though. All right, let's do another example here. Actually, not very much for me to write down here. But what we're taking a look at now are the 3 unit vectors I hat, J hat, K hat. I hat, J hat, K hat. What are their cross products between them? So let's go ahead and take a look at our friendly I hat, J hat, K hat vectors. So here's I hat, which is 1 unit in the positive X direction. J hat, which is 1 unit in the positive Y direction. K hat, which is 1 unit in the positive Z direction. All right. So remember that the magnitude of the cross product is the magnitude of the one vector times the magnitude of the other vector times the sine of the angle between them, right? And then you use the right-hand rule to figure out the direction. Now, if we were to take I hat cross J hat, so I hat cross J hat, the thumb would point up, right, in the positive Z direction. What would be the magnitude of I hat cross J hat? 1, exactly. Because the magnitude of I hat is 1, magnitude of J hat is 1, and the sine of 90 degrees is 1 as well. 1 times 1 times 1 is 1. So I hat cross J hat, that result would be a vector of length 1. Hi, come on in, find a seat. And point in the direction of K hat. So it must be K hat. So I hat cross K hat, J hat, I mean I cross J is going to be equal to K. And likewise, K hat cross I hat is going to be J hat, and so forth. So here's actually a little diagram that I learned a long time ago, and it's extremely useful. And so the first several times that you take a quiz or a test involving vectors and you're not quite practiced on taking cross products of vectors, this is a handy sort of device to help you remember how to take cross products of unit vectors. So here's how this goes. You notice you've got I hat, J hat, K hat, and then these arrows go in the counterclockwise direction. So how this goes, you got I hat cross J hat is equal to K hat. J hat cross K hat is equal to J hat. I hat, I mean. J hat cross K hat is equal to I hat. And then K hat cross I hat is equal to J hat. And so, but now, if you go in the opposite direction, then you induce a negative. So I hat cross K hat is equal to negative J hat. K hat cross J hat is equal to negative I hat. J hat cross I hat is equal to negative K hat. Okay, so now we are about to talk about, and we already talked about this. We're ready to talk about how to do the actual computation of cross products. Now, here's probably the most straightforward way of computing the cross product of two vectors U hat, or U and a V, U cross V. Now, some of you have already had some experience with matrices and some not. That's okay, I'll just talk you through this. How to compute the determinant of a 3x3 matrix. Now, when you see this 3x3 grid of numbers, this is a 3x3 matrix, 3 rows by 3 columns. And when you see these parallel bars on either side of this grid, that means that you're taking the determinant. And you don't necessarily have to know exactly what a determinant is, but of a matrix, but you're doing an operation on this matrix, which is, and the determinant of a matrix is somewhat remotely akin to like a size value of a matrix. But here's how we do this. Here's how we set up this matrix in order to compute the cross product of U and V. Across the top row of this matrix, we write I hat, J hat, K hat. And then U, the components of U, will go in for the second row. And then the components of V will go in for the third row. Now, here's how we compute the determinant. Now, we do it by a system of cofactor expansion. Now, I'll tell you exactly what that means. We start across the top row, starting off with I hat. So we're going to take I hat times, and then what it is that you take times is that you're going to take the determinant of a subset of this matrix. And the subset is determined by, well, let's see if I can do it with these erasers here. You blank out the column that I hat is in, and you blank out the row that I hat is in, and then you take what's left over. In this case, you get the rest of the U, or the second row and the third row minus its first column. So this little 2x2 matrix here, that's the minor. So and then you take the little determinant of that 2x2. I don't know. And the determinant is basically just going to be, you know, this number times this number minus this number times this number. I'll show you here in a few minutes. And then, as you work your way across the top, your next stop is here at J hat. But you need to put a minus in front there, so there's a minus in a J hat times the determinant of its minor. And its minor is, well, block out the row and the column that includes the J. So blank out the top row and the middle column, leaving you with the, you know, with the U1, V1, U3, V3. And then finally, we are over here with K hat. And then it's minor, block out the top row and the third column, leaving you with this little 2x2 matrix in the lower left. That is its minor that you'll be taking the determinant of. So this is what you have as the computation of the cross product. So we've got some number times I hat minus some number times J hat plus some number times K hat. But what are these numbers? Looks kind of mysterious at first, but folks, It's just a matter of taking the determinant of these little 2x2 matrices. Oh, and like I said, how you compute the determinant of the little 2x2 matrix is you take a U2 times V3, for example, minus V2 U3. And that'll just do the number. For example, you do the same thing for the other two matrices, and you'll have your vector, which is cross product of U and V. So let's do an example. Example number 3. At the top of page 815. And so by means of an example, we're going to actually compute the area of a triangle. So what we've got here is we've got 3 points in space. We've got a point O with coordinates 0, 0, 0. So the vertex, well, we have one vertex of the triangle at the origin. And then we have a point P at coordinates 2, 3, 4. And we have point Q at 3, 2, 0. Now, so like I said, you need to think about this triangle in three-dimensional space. This might be O, P, and Q here. So find a vector that maybe goes from O to P, and that goes from O to Q. And then take the cross product of OP and OQ. And you don't have to do OP and OQ. You could do, PO and PQ, or QP and QO, or whatever. But just make sure that your two vectors have a tail at the same vertex. Okay. So let's find vector OP, which is the vector that goes from O to P. And that one's easy to find because the tail is at the origin. So there's OP. Okay, now let's find OQ, and that's pretty easy to find too because its tail is also at the origin. So that has component 3, 2, 0. Now let's find the cross product, of those two vectors. All right. So here's our little 3x3 matrix, I hat, J hat, K hat. And then we'll take OP first, components of OP 2, 3, 4. And then the components of OQ 3, 2, 0. Now, we'll start off with I hat up here, and its minor is the 3, 4, 2, 0 times I hat. And then minus, the minor for J hat is going to be the 2, 3, and the 4, 0. J hat, and I need to go down here, plus for K hat, we've got its minor of 2, 3, and 3, 2, K hat. Now, equals. Now, this determinant right here for the I hat, you got 3 times 0 minus, so that's 0, minus 2 times 8. So 0 minus 8, I hat. And then minus the determinant for the J hat piece, 2 times 0, which is 0, minus 3 times 4, which is 12. J hat. And then plus for the K hat piece, we've got 2 times 2 is 4, minus 3 times 3 is 9. Now, let's finish this off. 0 minus 8 is negative 8. So we have negative 8 I hat minus, now, we have 0 minus 12 is negative 12. And the negative of that is positive 12. So we have 12 J hat. And then plus negative 5 K hat. Now, let's go ahead and take the magnitude of OP cross OQ, square root of negative 8 squared, which is 64, plus 12 squared, which is 144, plus negative 5 squared, which is 25. And what does that work out to be? So 233. Square root of 233. And so the area, well, the area of the parallelogram that has, two adjacent sides defined by OP and OQ is square root of 233. But if you take half of that, then you get the area of the triangle. So area of triangle is equal to half of that, square root of 233 over 2. Whatever that is, but it's an exact number. Have you noticed that my math lab sometimes prefers exact numbers in the form of radicals and everything? So have you discovered how to use the little palette in the upper left of the My Math Lab screen? How to input your radicals and stuff? Okay. So here's a picture of what we just did here. We had point O, point P, point Q, and here's the three-dimensional triangle. We just found the area of that. Which is 1/2 of the magnitude of the cross product of vectors OP and OQ. All right, let's do another example here. This example number 4. We've got two vectors, U, which is negative I hat plus 6K hat. Now, I like to fill in missing components by putting a 0 as the coefficient there. So instead of writing negative I hat plus 6K hat, I would prefer to write negative I hat plus 0J hat plus 6K hat when I'm about to do some sort of computation involving these vectors. So we have plus 6K hat. And then we have a vector V, which is 2I hat minus 5J hat minus 3K hat. And what we need to do is find a vector that is orthogonal to both of these vectors. And that vector would be some multiple, any multiple of U cross V or V cross U, whatever. So if you want a vector that is perpendicular to both U and V, then just take U cross V. All right, so here we get a little bit more practice in computing the cross product here. So here's our little 3x3 matrix that we're going to compute the determinant of. Across the top row we have I hat, J hat, K hat. Second row consists of the components of U. So we have negative 1 from the coefficient of the I hat term, and then we have 0, and then we have 6. And then we have the components for vector V, which is 2, negative 5, negative 3. Now, we're going to go through this a little bit more quickly, okay, in computing the cross product. Starting off for I hat, All right, so you could just see the little minor right here embedded within the 6x or a 3x3 matrix. Is this little 2x2 thing? What's the determinant of that? 0 minus negative 30, huh? So that's positive 30. So we have 30 I hat. All right. And then moving over to here, j hat, automatically write a minus. And then the minor for j hat is this piece together with this piece. You can take the determinant by taking this negative 1 times negative 3, which is 3, do a little scratch work there, minus 2 times 6, which is 12. So 3 minus 12. 3 minus 12 is negative 9, j hat. Let me erase that. Scratch work there. And then moving over to k hat. Moving over to k hat here. Here's the minor for k hat. Go ahead and take negative 1 times negative 5 is 5 minus, and then 2 times 0 is 0, so it's just going to be 5. So plus 5 k hat. Any questions on how to compute that cross product by doing the determinant? Practice it, folks. Do lots of practice, and you just zip right through it. So this cross product, this cross product is 30 I hat plus 9 j hat plus 5 k hat. So any multiple, any scalar multiple of this vector is orthogonal to both u and to v. So if you were to take half of it or 10 times it or whatever, it'll be an orthogonal vector to both u and v. So now that we know a little bit about cross products of vectors, let's now turn our attention back to the torque, which is one application of the cross product. So we already did that. All right, torque. All right, so we have our lever, which is indicated by this radial vector r. That points from where the actual twisting is happening, basically where the bolt head is, out to the end of the lever. That's what R is. And then from the head of R, we have the tail of your force vector. Yeah. The force vector is basically the force that you are applying to the end of the wrench to either tighten or loosen that bolt. And then, of course, we have this angle that's made between the direction of the force and the direction of the lever. Now, from your everyday experience, can you really do a good job in applying torque to anything if you are doing it in actually the direction of the lever? No. I mean, if you have this, I don't know. So if you have this lever here and you're pushing in at it or pulling on it, are you going to twist anything? No. But if you were to apply a force at 90 degrees, that's where you'll have your biggest impact, right? So you have R and you have F, either pointing down or pointing up. So if that angle is 90 degrees, then you'll have maximum torque, for a fixed length lever R, and a fixed force. So that optimal angle is going to be 90 degrees. Let's take a look at example 5, how we can compute torque. It's basically computing the cross product of force and R. Now, they use tau as the vector for torque. Okay. Now, tau is equal to your lever vector crossed with the force vector. Now, example 5, they have a discussion of it at the bottom of page 815. We're going to tighten a bolt by using a wrench. We are going to apply 20 newtons of force to a wrench. So we are given that the magnitude of the force vector is 20 newtons. And this force is applied in a direction that's perpendicular to the bolt. Now they're asking which produces more torque. Applying the force at an angle of 60 degrees on a wrench that is 0.15 meters long, or applying the force at an angle of 135 degrees on a wrench that is a quarter meter long. In each case, what is the direction of the torque? Well, that's easy. That's in the direction of the bolt. For that direction. But let's compute the magnitudes for each one of those scenarios here. Now, for the first scenario, what was the angle? 60, right? And the length of the lever was 0.15. 0.15 meters, and the angle was 60 degrees. So the magnitude of the torque will be magnitude of the force times the magnitude of R times the sine of the angle between them. Well, I should just call that theta, huh? It's always good to start off with the basic set. So, but magnitude F is 20. Magnitude R is 0.15 times the sine of 60 degrees. What is the sine of 60 degrees? Square root of 3 over 2, right? Okay. So what does this work out to be? So you got 20 times 0.15 times square root of 3 over 2. And that works, I guess, about to be a 2.6, right? 2.6 Newton meters. What is a Newton meter, by the way? Anybody? That's another way of saying a Newton meter. Huh? Yeah. So you could say a Newton meter or joules. B. Let's compute the magnitude of the torque for the second scenario, where the length of the lever is 0.25 meters, and the angle is 135 degrees. So the magnitude of the torque is going to be magnitude F, which is still 20, times magnitude R, which is 0.25, times the sine of 135 degrees, which is square root of 2 over 2, or 1 over root 2, same thing. And what does that work out to be? You got 20 times 0.25 times square root of 2 over 2. approximately that's equal to what, about 3.5? So 3.5 Newton meters or joules. So you have in scenario A shorter lever but a steeper angle, but scenario B a longer lever and a shallower angle. And it's the second scenario that gives you the better torque in this case. And the direction, of course, is in the direction of the bolt. So this diagram is for the first scenario where you had angle 60 degrees and the length of the bolt of the wrench 0.15 meters. The direction of the torque is straight up through the bolt. And the direction of twisting, where the bolt is being tightened, it's going in the direction of the tightening motion. And this picture was for the second scenario. So, all right, moving along here. All right, this last piece is just for fun. And if you're not into physics or anything, you can kind of tune it out. I'm not going to talk too much about it. So, but if you have a charged particle like an electron or a proton or something like that moving through a magnetic force, well, it turns out that there is a force that's applied to it. So it kind of goes like this. Let me try to draw a picture for you. So here you've got this particle with a charge on it. Now, would it be a neutron? No, because it's neutral, right? But some other elementary particle that's got a charge on it, maybe a positive or a negative charge, and it's going in some direction, and then all of a sudden some magnetic field gets applied, and that magnetic field is indicated by a capital B, and it's a vector valued function. Well, there's going to be a force that's then applied to the particle that is dependent on the direction of travel by that particle, as well as the strength and direction of that magnetic field. And that force that's applied is given by, now what is Q? It's the charge. And is Q a scalar quantity or a magnetic or a vector value quantity? It's a scalar quantity, so it's the strength of the charge, times, so it's the scalar multiplier of V cross B. Now, V is the velocity of your particle. Remember, velocity is a vector valued function with the magnitude of speed, and the direction of the velocity gives the direction of travel at that particular point, wherever you're taking the velocity of. All right. So the force that's applied to this particle by this magnetic field is given by the strength of the charge on the particle times the cross product of the velocity of the particle and the magnetic field. So there's another application of the cross product. So if we have our particle moving in this direction, and suppose that the magnetic field is pointing up. So which way would the particle be forced to move? So point your fingers in the direction of travel of the particle, curl your fingers in the direction of the magnetic field, and then your finger, your thumb, your right thumb, will point in the direction in which the particle gets accelerated. So this is a different picture of the same thing. Here you've got your charged particle, magnetic field V. Your vector, your velocity vector is always in the direction of travel. So at this particular time, the velocity vector is pointing in this direction, where the yellow is the trajectory. So which way is the particle going to move? So V cross B. So here's V cross B, and of course it's hard to judge right now exactly where it's V and where it's B, but just use the right hand rule in three-dimensional sense, and that'll tell you the direction. But do you see how the yellow curve is pointing? Maybe it's pointing kind of in that direction, inward and downward, and it's probably because this force vector is probably pointing in this direction. Okay. But of course, as the particle changes direction because of the force, then it's going to have a different force applied to it because it changed direction, which is going to apply yet a different force, which is going to give a different velocity, meaning a change in directions and so forth. So interesting. So let's take a look at example 6. This is really interesting, is that you can get a particle go into an orbit just by trapping it in a magnetic field. So let's just take a quick look at example number 6. So here for example number 6, we've got a force on a proton. Proton that has a mass of 1.7 times 10 to the negative 27 kilogram. And the charge of Q is equal to 1.6 times 10 to the negative 19th coulombs. Let me go ahead and write those quantities down here. So we have mass is equal to 1.7 times 10 to the negative 27th kilograms. A charge of positive 1.6 times 10 to the negative 19th coulombs moves along the x-axis with the speed of, and here's magnitude V, there's speed of 9 times 10 to the 5th meters per second. So when it reaches the origin, a uniform magnetic field is turned on. The field has a constant strength of 1 Tesla and is directed along the negative z-axis. So it basically goes down. So let's see where we're at right now. Q is where our proton is, and it's moving in the direction of positive x-axis. So you see the velocity vector V, which is the red one. That shows that at the moment that particle hits the origin. And then you see the green arrow that shows the magnetic field, which points downward. So using the right-hand rule, V cross B, right? Which direction is that particle going to be accelerated? Here's V, cross V, and the thumb points, well, gotta do it in this direction, I guess, V V cross B, it's going to be accelerated in this direction. But of course, as it changes direction, the direction in which it gets accelerated is always changing as well. So it's going to travel from here to here. Let's just see where it is right here as it gets into this orbit, and now it's traveling in this direction, I guess. And then V cross B. So here's V cross B, and it's going to get accelerated this direction. So it's going to get moved this way. And look, because of V cross B, this particle is always going to be going around in a circle because of the acceleration. Going around and around and around and around in this endless loop. As long as that magnetic field is constantly going south, it's going to go around that circle. So let's just do part A, and I'll let you do part B on your own if you're interested. Part A for this problem is find the magnitude and direction of the force on the proton at the instant it enters the magnetic field. Now, the force is given by the charge times V cross B. So, and you can write magnitude of the force as Q times, magnitude of V cross B. But then you could write the cross product of V and B as magnitude V times magnitude B times the sine of the angle between them. Now, we know what Q is. Q is the, 1.6 times 10 to the negative 19th power. We'll leave off the units. So that's the Q times magnitude V, which is 9 times 10 to the 5th power. So we're multiplying still here. Times magnitude B, which is 1, times the sine of the angle. And sine of 90 degrees, because they are at 90 degrees to each other, is 1 as well. So it's just going to be the 6 times 10 to the negative 19th power times 9 times 10 to the 5th power. And that works out to be about 1.44 times 10 to the 13th power. Now, what direction is that? That's going to be negative k hat. Sorry, no, not negative k hat. It'll be what? Negative. That'll be actually positive j hat, because B is in negative k hat direction and V is in positive I hat direction. So I hat crossed with negative k hat is equal to positive j hat. So if you want a direction, it'll be positive j hat. So which matches this idea that that particle is being accelerated in that direction. Now, if you are interested in the part B, you can calculate the radius of the orbit by looking at this little equation that relates the centripetal force with the mass as well as the speed and the radius. So you could set that centripetal force function equal to this and solve for the radius. I'll let you do that on your own. We're done with section 12.4 as of now. When we come back from break, though, we'll do a little example together in class where you'll pull out a piece of paper and put your name on it and turn it in for extra credit at the end of class. All right, so let's take a 10-minute break. So here we're going to use the formula for centripetal force that says that the magnitude of force is given by mass times the square of the speed divided by the radius of the orbit. So use that together with the equation from the magnetic force on a moving charge, which says that the magnitude of force is equal to the absolute value of the charge times the speed times the magnitude of the magnetic field times the sine of the angle in between. So use those two equations to find the speed of our electron in problem 67. Okay, so I'll give you a couple minutes to talk about it with your neighbor, and maybe draw a picture on that piece of paper that you pulled out and put a name on it that you're going to turn in at the end of class. And it's okay for you to collaborate with your neighbor.
What we're trying to find over the basis.
The strong proponent of proof.
We know F has got to be very important. We don't know B squared over Y squared B.
You don't have an English to collaborate with. You're over here by your lonesome. Another clue would be that is that you could set this equal to that and solve for magnitude v, right? Because you are solving for speed, right?
Yeah, so one of the piece cancels, and you know. This is chemistry. So that's not a topic, that's just an interpretation. Because it is, yeah. So these piece cancel, okay? Because it's all just multiplication.
Okay. So you've got two equations where the magnitude of the force is equal to something, right? Now, you're not given the magnitude of the force either, are you? But you could set the right-hand side for both equations equal to each other. So you could set mass times speed squared over radius for the orbit equal to absolute value of the charge times speed times magnitude of magnetic field times sine of angle equal to each other. By the way, the angle is pi over 2, right? 90 degrees, so sine is 1. You can cancel one factor of the speed from both sides and then solve for the remaining factor of speed on the left by multiplying both sides by r, divide by m. And you know all four of these quantities, don't you? So plug in the numbers and it works out to be about 1.8 times 10 to the 7th. And because of the fact that the quantities given are in terms of standard units, right, SI units, then the resulting speed is going to be in, have the units meters per second, right? Right? Okay. I know it's more of a physics sort of problem, but you know what? There's such a strong interplay between calculus and physics that it's hard to separate the two. Yes?
Do we need to know like these types of formulas?
No. If I wanted you to know that for a problem on a test, I'd give it to you. It's not something that you would have to memorize, all right? All right, so it's an application of the cross product, all right? So, yes, Cal? Yes. That information's on the syllabus, crib sheet. Yeah, 1 8.5 by 11 sheet of notes for each test. Yes?
When is our first class?
I haven't set a date yet. But it'll probably be before I leave town if I go on that trip to South Carolina that I was contemplating. By the way, if I do go on the trip to South Carolina in June from about the 16th to the 28th, I know who your substitute will be. The first letter of his last name starts with W. And the last letter of his last name is U. It's not Doctor Who. It's Doctor Wu. I didn't choose him. But it's the same scenario last year because when I went to annual training, he covered my Calc 3 classes and enrollment fell by about half. But they came back eventually. He's a good guy. He's just misunderstood, right?
Does attendance count?
What's that?
Does attendance count when you're not?
Homework does. So you could be a proxy. I don't think he records lectures like I do, though. Look, he is a good guy, very smart. It's just that a lot of people don't click with him, though. Just a different sort of teaching style and learning style. Okay? All right? Just understand that. Yes?
Are the homework assignments going to be 60 questions the entire year, or is that just to start us off?
Okay. I think I've already mentioned already. I give you guys all the problems that they have, so if there are some problems that you don't like, just skip them. But what I typically do is that for about 75% of the points that are available is what would be about 100% for the homework. All right, does that make sense?
Yeah.
All right. So just do as much as you can, okay? I'm just giving you all the problems that are available for you. So get in there and have fun and just do as much as you can, okay? Now, look, every one of us is coming from a different background, right? We all have our different strengths and weaknesses. Just do as much as you can, learn as much as you can. We're all here to learn. I don't want anyone here to be bored. Questions?
So does that mean if we earn 75%?
Approximately, yeah.
Okay.
Yeah. My grading scheme is a little bit loose and flexible. How's that? Okay. But people who've taken my class in the past know that I'm a fairly reasonable grader. Okay, right? Okay, just learn as much as you can and try not to game the system. Because I know that we're students, right? I was there myself, and we all like to try to game it. So we have to do as little work as possible to get an A, right? Just focus on learning. I know. Yeah. So I recognize it, but folks, just focus on trying to learn some math, okay? But look, here's the thing, though. You can get away with gaming it only for so long, and then you're going to be expected to know something when you get out there and actually have a job as an engineer or a scientist or a mathematician or statistician or whatever it is that you're going to do. And you're going to be expected to know a few things instead of being a good manipulator. Question? At the end of class. All right. Now we're going to talk about three-dimensional geometry a little bit more, but this time we're going to focus on these creatures, my term, called vector valued functions that we're going to use to help define lines and curves in three-dimensional space. Now, before I flip to the next slide, think about what is the basic sort of standard form of an equation for a line in two dimensions? Y equals mx plus b, or ax plus by equals c, or something like that. Well, what would it look like if you had to write something for a three-dimensional line? Would it be like ax plus by plus c z equals d or something like that? The answer is no, because that would be a plane. A line is a one-dimensional object living in two dimensions, right? When we're talking about a two-dimensional plane with a line, right? And a plane is a two-dimensional object that's living in three dimensions. But now we need to come up with the equation of a line in three dimensions, and it's a one-dimensional object living in three dimensions. So we have to use parametric equations, or at least some facsimile of a system of parametric equations to define a line in three dimensions. And this is where a vector is going to help us. For example, before we talk about lines, let's just generally talk about any curve in three dimensions. A line just happens to be a straight curve. Well, we've talked about any curve, which is, you know, essentially two-dimensional. Actually, it's one-dimensional in three-dimensional space, actually. It's a one-dimensional object in 3 dimensions. Anyway, so here's kind of how we think about this. Look at this position vector that goes from the origin out to some point. Call that our R vector. R as in like a radial sort of vector. With components x, y, z, if the coordinates of this point is x, y, z. And then think about then the x, y, and z coordinates of this point changing with time. As in x, y, and z are functions of a common variable time. So as time changes, the coordinates change. So then we would have this curve that gets traced out as t changes. And for different values of t, you'd have a different radial r vector that goes from the origin out to whatever that new point is. And that collection of those points would define the curve in 3 dimensions. So you can think about this vector r, where each of the components are functions of t, as a vector valued function. Vector valued function where it's a function of t and it's a vector. Give me a different value for t and I'll have a different vector. I'll be at a different point on the curve for different values for t. So that's how we can determine a curve in 3 dimensions, is having this set of parametric equations, right? Now, the last topic that we covered in Calc 2 for this campus, or for DMAC, is parametric equations. Well, you can kind of think about the vector value function as having those parametric equations for their respective components for the vector. It's a real handy way of defining curves in space. A line just happens to be a particular curve that is straight. So here's kind of the idea here. You can kind of see this picture. It's the same picture that you see in your book. So you've got some point that the line goes through. That point has coordinates x naught, y naught, z naught. It's a fixed point. And then let's just suppose that we want to come up with the equation of the line that goes through that point in a certain direction. Maybe parallel or in the direction of a given vector, v, which is the green vector. Let point P be some variable point that's on that line that goes in the direction of V through that given point. So here's your variable point P. It's variable, it's like a V, you can kind of adjust it anywhere you want. But this point P sub 0 is fixed. Now, typically you're going to be given a direction vector V. It's like, I want the equations of a line that goes through this point and in this direction V. So you need a vector and a point to define a line in 3 dimensions. Say it again. Write this down. You need a vector and a point. A vector and a point in order to define a line in 3 dimensions. A vector and a point. The vector will give you the direction of your line. And of course, the point will tell you, specifically where in space that your line needs to go through. Now, you look at this vector that goes from the origin out to that specific fixed point P sub 0. Call that vector OP, or OP sub 0, I should say. and then we have this variable point P, and you look at the vector that goes from P sub 0 out to P, and that's going to be some multiple of vector V. That multiple is going to be T. So, going back to this red vector that goes from the origin out to that point P, well, the origin has coordinate 0, 0, 0. So you can think about that vector that goes from the origin out to P sub 0 as that vector that has components with the coordinates x sub 0, y sub 0, z sub 0. And instead of calling it OP sub 0, call it R sub 0. So you take R sub 0, which is the red vector, together with T times V, add those two vectors together to get your R vector that goes from the origin out to that variable point, and then here you go. You've got your R vector, which is going to be the vector valued function for your line in three-dimensional space. Okay? So, I think we should do an example, huh? See how this goes. You're going to be given some vector V as your direction vector components ABC. And you're going to be given a certain point in space that the line goes through, x sub 0, y sub 0, z sub 0. So all you need to do is just add these two vectors together. So you'll have a new vector, x sub 0 plus t times a. That will be the x component of the resulting parametric equation or vector value function. Y sub 0 plus t times b for the y component. Z sub 0 plus t times c, or c times t for the z component. So you could either think about this as a set of parametric equations for your line in space, or you can put them together as components for an R vector valued function. Now, because of this, the fact that we didn't specify any sort of ray or line segment or anything, if this is a line that goes forever in both directions, then we'll assume that t is some real number that goes from negative to positive infinity. All right, Moonal, let's do an example here. Example number 1. Find an equation of the line that passes through the point P sub 0, 1, 2, 4 in the direction of vector V (5, negative 3, comma 1). Well, your x of t is going to be the 1, which is the x coordinate from your point, plus t times 5, or 5t. The 5 being the x component of your v vector, of your direction vector. Your y of t is going to be the 2 minus 3t. Your z of t is going to be equal to 4 plus t. But you can write this as your vector valued function. And of course, no parameterization is complete without specifying a range of values for t. That range of values applies both for the set of parametric equations And, it would be implied for your R function that all values of t are game, unless you want to limit that line to some segment or array or whatever. But there you go. That's how you write your line in 3 dimensions. If you know your point and a direction vector. Take a look at example 2. Well, there's a picture of what we just did. For example 1, here is a point, and there's a direction vector. And we just found the vector value function, which describes that line that goes through that point in the direction of that vector. What you see down here at the bottom is if you were to project this line down onto the xy axis, xy plane, on the xy plane, the z is equal to 0. So if you were to take the r vector and set z equal to 0, then you would just have 1 plus 5t for x, 2 minus 3t for y. If you were to eliminate the t parameter between those two, we could solve for y in terms of x. And you would have this equation of the line in the xy plane. That would be like if you were to shine a light on top of the line, and this line down here would be the shadow of that line on the xy plane. Moving along here. Example 2. Find the equations of a line, or the vector valued function equation for a line that goes through 2 points. P sub 0, which has coordinates -3, 5, 8, and P sub 1, 4, 2, -1. So it goes through those 2 points. It doesn't say in what direction, because it doesn't matter. It's a line, right? So we're assuming that line goes forever in both directions. So we can come up with a vector that goes from P sub 0 to P sub 1, or P sub 1 to P sub 0. Doesn't really matter. Let's just come up with a vector that goes from P sub 0 to P sub 1. And that'll be our direction vector. Remember, what is it that you need to define a line in 3 dimensions? A vector and a point. Well, you got 2 points here, but hey, you can come up with a vector that goes between those 2 points. So the vector that goes from P sub 0 to P sub 1 is going to be 4 minus -3, which is 7. 2 minus 5 is -5. -1 minus 8 is -9. -3, yes. I was just checking to make sure that you're paying attention. And you were, so you get a cookie. Alright, so there's a direction vector, and you could choose either one of those points. You'll still, as long as you let t go from negative to positive infinity, you'll still have your line. So if you use the first point, P sub 0, then you have your x of t is going to be the -3 plus 7t. You have your y of t is equal to 5 minus 3t, and your z of t is equal to 8 minus 9t. Or writing as your r vector, put it all together, -3 plus 7t, 5 minus 3t, 8 minus 9t. What is t? It's parameter, right? And the range of values for t is from negative to positive infinity. So for all real numbers, if you have an infinite line in both directions. Okay, any questions on example 2? those of you who are scrambling to take notes, I save these annotated slides on Blackboard, so you could always pull these down later. And I saved the recorded lecture on Blackboard too, so you can always go back later and watch the video. It's posted on Blackboard as well as on YouTube. Just check your DMAC email later. All right, so the black line here is that line that we just found the equation for. Now, if you wanted to find that portion of the line that's projected on the XY plane, that's the blue one, by, again, setting the z component equal to 0, and then eliminating the t parameter from the x and y components and solving for y. Or if you wanted to find the projection of this line onto the xz plane, then you can eliminate the y component, and then, or set the y component equal to 0, and then you have the x and z component. Eliminate the t variable between them and solve for one variable in terms of the other. All right, and that's kind of what they're doing there. They're projecting the line onto the xz plane by eliminating the y component and solving for z in terms of x. Not of very much interest to me, so moving along here. Example number 3. Now here we're going to just be interested in the line segment that goes from one point to another point. So suppose that we've got 2 points in space, p sub 0 with coordinates 3, -1, 4, and p sub 1 with coordinates 0, 5, 2. And suppose that we want to find the equation of the line segment between these 2 points. So again, we need a vector, and of course we've got 2 points. So let's again find the vector that goes from p sub 0 to p sub 1. So 0 minus 3 is -3. 5 minus -1 is what? Ashlyn? 6? Okay, just checking. 2 minus 4? -2. Now let's go ahead and write your R of t vector just for the general line, and then we'll figure out what it is for the segment. Now R of t was going to be, now using the point p sub 0, like I said, we could just as well use p sub 1, but we'll use p sub 0. 3 minus 3t for the x component, -1 plus 6t for the y component, and then 4 minus 2t for the z component. Notice the beauty about this is that when you set t equal to 0, meaning r of 0, then what do you have? Then you have 3, -1, 4. And not only that, what do you have when you have t equals 1? When t is equal to 1, meaning r of 1, 3 minus 3 is 0, -1 plus 6 is 5, and 4 minus 2 is 2. You happen to be at p sub 1. So all we need to do is just specify the range of values from 0 to 1 for t. And boom, there, we've got our line segment. There's our line segment. Does that make sense, everybody?
Any questions on that? Okay. And there's a picture of what we just did. Point P sub 0, P sub 1. And we came up with the line segment that goes between those 2 points. And of course, you could project that line segment into any of the 3 coordinate planes by setting the appropriate variable equal to 0, or variable component. Moving along here. Now, moving beyond lines, let's just talk about curves in general. Of course, as we have R of t equal to, these 3 components for the x, y, and z components, they're all functions of t. And over some range of values for t. And this will trace out some curve or segment of a curve in 3-dimensional space. All right? This R is also a function, so a lot of the analysis that we do in calculus for functions apply, including finding the domain and range of a function, taking limits, taking derivatives, integration, and all the other fun stuff that we know and love from algebra and calculus. All right? What do you think the domain of this vector valued function is? Well, what is the domain of any function? It's the range of allowable inputs for the independent variable, huh? Well, that's the same thing here for the domain of this function, of this vector valued function, except we need to take a look at each of these 3 individual functions for the components. So the domain will basically be, well, look at the domain for f, look at the domain for g, and look at the domain for h. And then the domain for R overall will be the intersection of the domains for each of the 3. So it's the smallest range of values or collection of values for t that would make f and g and h defined at the same time. But if there's any particular value for for t, I should say, that makes at least one of those components undefined, then that whole vector valued function is undefined. Okay? So you'll have the chance to play with that on the homework. All right. Now, we need to just talk real quick about orientation. Now, orientation of a curve in 3 dimensions or even 2 dimensions is implied by the parameterization as indicated by, what direction is the curve evolving as you let t increase in value. Now, if we have an unparameterized curve where we just don't really care, what t is, and so how the curve evolves as t increases, then we just have some curve in space, and so you could have a tangent vector that either points in the one direction or the other, as long as it's a vector that is tangent to the curve. That's really the first time that we've used that term, right? Tangent vector. We know what a tangent line is, and we know what a vector is. So what do you suppose a tangent vector is? Well, it's a vector that happens to be tangent to the curve at some particular space. It's the same concept that you learned back in Calculus 1, right? What a tangent line is. It goes in the direction of the curve at that particular spot where the line hits the curve. where the slope of the line and the derivative of the function match at that exact point. Anyway, but if you have a parametrized curve, there's only one tangent vector that is going to be in existence. Anywhere, it's going to point in the direction of evolution of the curve as t increases in value. So, for example, suppose that we've got this unit circle, and we could define an r of t in 2 dimensions by what? Cosine of t, comma, sine of t. Now, for this one, as say maybe t goes from 0 to 2 pi, we start off here at 0, at t equals 0, and as t increases in value from 0 to 2 pi, it goes in this direction, counterclockwise. At pi over 2, of course, we're up here at 12 o'clock. At pi, we're over here at 9 o'clock. And at 3 pi over 2, we're down here at 6 o'clock. All right, and of course, the whole time we're going counterclockwise. And then when we're back at 2 pi, when we're at 2 pi, we're back over here at 3 o'clock. But there's a direction implied as we let t increase in value. So that's what tells you the direction of the tangent vector at any particular point on the curve. So that's kind of what we mean by orientation of a curve, is by what direction does the tangent vector point. Let's take a look at example 4 at the bottom of page 823. Basically, what we're taking a look at is the graph in 3 dimensions of this space curve. We have r of t is equal to 4 cosine t I hat plus the sine of t j hat plus t over 2 pi k hat. Now, it's hard to visualize in 3 dimensions, isn't it? Even in today's world, because, how much of the media that we consume, especially electronic media, is in 3 dimensions. It's usually on a flat screen, huh? So we're still so used to seeing the world in 2 dimensions. And it's even worse for people who have problems with depth perception, huh? But in this class, you're going to increase your ability to visualize in 3 dimensions. Now, one way that you can visualize a space curve as it evolves is by temporarily setting one of the components equal to 0. In this case, let's just set the z component equal to 0. So this part right here, just ignore it for now. And just focus on the 4 cosine t I hat plus sine of t j hat. Now, remember back when we talked about parametric equations at the end of Calculus 2. And when you have x of t is equal to 4 cosine of t and y of t is equal to just sine of t, all right, that parametric curve is an ellipse. And there's the graph of it. It just goes round and round and round and round and round as t goes around every multiple of 2 pi in the counterclockwise direction. And now bring back in that z component of t over 2 pi. Now, if we just temporarily let t go from 0 to 2 pi for that entire space curve, then z component is going to go from 0 to 1 because t goes from 0 to 2 pi. Z goes from 0 to 1. So in the z direction, that height of that curve goes from down here at ground level up to z equals 1, which is where you're at right here. Where you started off down here, and then you climbed up the hill. And then, of course, as t goes beyond 2 pi, this thing is going to keep spiraling up in an elliptical fashion, like you see here. But the x and y components are just going to be stuck in that elliptical loop, while the z component, it continues to increase in value in a linear fashion. So there you've got this three-dimensional corkscrew that's elliptical. It's like taking a spring and squashing it laterally a little bit, huh? I think I did that at one time as a kid when I sat on a slinky. Great. All right, let's take a look at a different space curve. This is example 5. Let me pause real quick. There have been some people who've asked me about accessing interactive media content in my math lab. There's some interactive stuff where you can do problems in my math lab using interactive figures or using the chapter content material. Now, you need Wolfram CDF player. Let me write that down for you. Wolfram CDF player installed on your computer. Wolfram. So if your computer doesn't already have the Wolfram CDF player, and you want to interact with the interactive material on my math lab, then just go on the internet, go on to Google or Bing or whatever your search engine of choice is, and do a search for the Wolfram CDF player download, and then just go to the website and download it and install it on your computer. Okay. They'll ask you your email address and the name of the school. And it'll also, after you click on download, they'll ask you, why is it that you're downloading? And just say that you need it for my math lab or whatever. And you'll probably get a follow-up email message from the company asking you if you're interested in Mathematica or something, and you could probably just tell them no thanks. Whatever. That's it. But that software is what your computer needs to use the interactive content. Okay. All right. So for this example here, we're going to examine this vector valued function. Cosine t plus sine t, or cosine ti hat plus sine tj hat plus 0.4 sine 2t k hat. So again, set the z component equal to 0 first, and of course you have cosine t for the z component, for the x component. I mean, sine of t for the y component. So you probably recognize it as a circle, right? And then the z component is going to vary sinusoidally with a period of pi, up and down with an amplitude of 0.4, right? So it shouldn't be too much of a surprise that you're going to have this interesting three-dimensional loop for your space curve, going round and round and round and round. Okay? All right. Example 6 is even more interesting. They call this a slinky curve. We're not going to do too much with this, but just take a look at the, this is the graph of the curve r of t is equal to 4 plus cosine of 20t times cosine of t I hat plus quantity 4 plus cosine 20t times sine of t j hat plus 0.4 times the sine of 20 t k hat. Okay. Now, again, in order to try to make sense of what this would look like in 3 dimensions, we can temporarily set the z component equal to 0, or just hide it. So set this, or eliminate the z component part right now, and just examine what it is in the x and y components. And here's the picture of it as t goes from 0 to 2 pi. Really crazy looking, huh? So you have periods within periods. Now the cosine of 20t, that has a period of what? Pi over 10, right? On top of this regular cosine function that has a period of 2 pi, as well as for the sine function that has a period of 2 pi. So it shouldn't be a surprise that you got squiggles on top of the squiggle of those one squiggle. These squiggles, these individual small squiggles, comes from the 4 plus cosine 20t, which is modulating the overall sinusoidal wave from the cosine of t and sine of t. Okay? And then we have the z component here, which adds, of course, that third dimensional complexity. So, of course, you can graph this using a computer algebra system like Maple or Mathematica. And this is kind of what it looks like in 3 dimensions. Crazy. Now, if we did not have parametric equations and or vector valued functions, we wouldn't be able to define these curves in 3 dimensions. Okay, moving along here. This is what it looks like basically looking down from the North Pole. So you go way up the z-axis and look back down, and that's what the curve would look like. All right, we have just one last little bit here. Like I said, your r function, meaning your vector valued function, it's a function. So everything that we've done with our normal scalar functions, we also can do with our vector valued functions. And that includes limits. And when we take the limit of a vector valued function as t approaches some number, we're taking the limit of each of the individual components. So basically, look, if you have r of t is equal to your, x of t, comma, y of t, comma, z of t, then your limit as t approaches a of r of t would be the same as your vector limit as t approaches a of x of t, comma, whatever that is, limit as t approaches a of y of t, comma, whatever that is, and then limit t approaches a of z of t. So you just take the limit for each of the individual component functions. So let's take a look at example 7. on page 826. So suppose that we've got r of t is equal to cosine pi t I hat plus sine of pi t j hat plus e to the negative t k hat for t greater than or equal to 0. So we have a couple of pieces for this problem. Part A, evaluate the limit as t approaches 2 of r of t. Okay, well, let's see here. That will be the same as taking the limit of each of the individual components. So, look, when you let t approach 2 for cosine of pi t, you have cosine of 2 pi. Now, cosine function is continuous everywhere. So, you could just evaluate the cosine function at 2 pi, which is 1, right? Okay. And what about sine of 2 pi? 0, okay. And then the exponential function is nice and continuous everywhere. What is the exponential, at 2, right? So we have e to the negative 2, right? Whatever that is. It's just some small number. So, hey, look, each of the components are nice continuous functions. So you just plug the numbers in. That's how we know how to evaluate limits of continuous functions. So, yes.
How do we handle it if the limit doesn't exist?
Then the limit won't exist for the, right. B, evaluate the limit as t approaches infinity. Okay? Now, cosine function, is that function headed anywhere as t goes to infinity? No, it's just going to oscillate up and down. So does the limit exist? No. Same thing for the sine function. Now for the exponential, that limit's going to be 0, right? But the overall limit does not exist because the x and y components will just go up and down, or they'll oscillate, right? Okay. C. At what points is R continuous? Well, we need to take a look at the continuity of the individual functions. And just like for the domain, the intersection of the sets of t for which the individual components are continuous will be the set of continuity for R. But in this case, all three functions are continuous everywhere for all values of t. And not only that, t is restricted, though, to non-negative values for t. So we say that R of t is continuous for all t greater than 0, greater than or equal to 0. Okay? Now, in the book, they say R is continuous for all t. But, again, by the definition of the function, we're restricted to the non-negative values for t. So, but I don't mean to split here. So, all values of t, all values for t greater than 0. It's all good. All right, so that's it for now. Now, I'm going to end this. Now, if you need to go take a little break real quick, you can.